we introduced last semester kinetic. Kinetic, kinematic. Kinematic, so kinematic. Kinematic. That was the ratio of viscosity and density. So this kinematic viscosity is same unit of thermal diffusivity alpha. So this. So we could find that this like an analogy of the momentum transfer and heat transfer when we compare the thermal diffusivity and kinematic viscosity. And we introduced this dimensional value. This is Randall number. So this could be rewrite. Excuse me. It's different. Opposite. Kinematic. Okay, this is a Plato number, ratio of the kinematic viscosity and thermal conductivity, thermal diffusivity. So this dimensional value, dimensionless value, sorry, is the relative ease of the momentum energy transport. So this is momentum. This is heat. So when we have large Randall number, the momentum transfer is large. However, if we have small Randall number, the heat transfer is relatively large. So let's go to the example of the 9 to 1. We have two plates. So 0.252 inch and heat is transported the area of the plate is 1 square feet, and this is the temperature 1. This is a temperature 0. Okay. So because of the British unit, we have to convert several units to the SI unit. I'm just rewriting now. The y Q is the heat flow. So finally, I didn't read the problem, sorry. Page 258 is example 921, measurement of thermal conductivity. So a plastic plate, a plastic panel of area equal 1 feet square meter, 1 square feet, and thickness y equal 0.252 inch was found to conduct heat at a rate of 2.10 watt at a steady state with temperature T0 24 degrees C and T1 26 degrees C imposed on the two main surfaces. What is the thermal conductivity of the plastic in the calorie per centimeter per second per Kelvin at 25 degrees C? So we can use the definition of thermal conductivity. I write here. So we can use this equation and we can derive, okay, it's Qi and delta T. So I don't write, but please understand the calculation found in the textbook. Okay. Oh, so this is very simple, but it's important problem when you start the study of the heat. The thermal conductivity can be measured by temperature difference and heat flow rate, etc. And we can calculate this value using this equation. Okay. So, okay. So this today is very common. We are going to go section 9.3. Work. So the energy flux involves the work flux. So let's see the textbook in the 258. The last energy transport mechanism that we will consider in this chapter is energy transported by doing work on a material. So I have to write a similar coordinate system, x, y, z. fluid is flowing this direction. So we define a plane on the ZX, so YZ plane, YZ coordinate system. So the work on the body is just this is just definition of work. So the fluid is moved to this direction. So this direction. So the fluid is done by work. The magnitude of the work could be explained. The product of the force and displacement. So we can derive the rate of doing work like this. So at constant force, we can say this one. So small displacement is divided by t. dt is just simply v, velocity vector. And so So based on the momentum flux tensor, we can extract the x component. This is a vector, the vector vector. In the product is this one, and this could be and similarly. So this is a momentum flux tensor. This is a y component. Okay. Rate of doing work by unit area. It's unit of vector. Simply in this. So this is a very simple situation that, so here is the definition of work. Work is the product of the force and displacement. So in the high school, you may learn this equation, much more simpler equation. Well, this is the rate of doing work. This is a time derivative, and we could find velocity because this small displacement of the time derivative. Time derivative of displacement is velocity, etc. So finally, we can combine the total three component of the energy flux. Total energy flux. Vector. Total energy flux vector is convective and conductive and work. And we have three components: convective, conductive, work flux. And this is the phi. What is the phi? Please remind. It was so that was the total molecular stress tensor. So we put this equation to this term. Because the P is scalar, and we need the vector. Oh. So this term to be combined with this internal energy term. So let's do that. So here, this is internal energy, phi unit mass. So you have multiplied by V plus EV. Because this is the unit vector, so we can omit delta. Can you understand? So we enclose this term by rho. So this term P is divided by rho means it's a B. Reciprocal of density is equal to the volume per unit mass. So this simple relation could be easily understood. So I don't know, you are familiar with thermodynamics, but this is the internal energy and PV. So this amount is the H? This is enthalpy. Enthalpy. Okay. So finally we could derive a final equation of the total energy flux. That is this one is the total energy flux. So you can find kinetic energy and enthalpy and molecular transport and conductive heat transport. Okay, so we have 30 minutes. So I want to skip the explanation of the equation 9, 4, 3, and 4. And could you open the textbook again? That's section 9.5. There are lists of the thermal conductivity from experiments. Okay? So if you have to solve the example problem and appendix problem, you may need thermal conductivity like say hydrogen at 100 Kelvin. That could be found in the table 951. The thermal conductivity is at 0.09, 0.69799, etc. Okay. And you can find some other leakage, something like this. So, because of time, we have to skip rest of this chapter. And let's go to the chapter 10. Chapter 10. Okay? So chapter 10, so the shell energy balance and temperature distribution in historical laminar flow. So we again introduce shell to develop equation, differential equation. So the shell balance is very simple. So when I write, because the temperature, heat is vector, not a tensor. So we are making a balance equation total out rate of work rate of energy production. So this is very simple. In, out, work, and production. 4 times. So then let's go to the chapter section 10.2, heat conduction in the steam pipe. So section 2 is very important to pass this lecture. So, can you see the textbook in the figure 10.2.1? So, we have 3 figures, A, B, C, and I explained today figure A only, and next week I will explain B and C. So what is the difference between 3 figures? Among 3 figures is the boundary condition. So now, here we have pipe, okay? Pipe. Then radius is R, sorry for very small p. The inner radius is kappa r. Okay, and we want to discuss about the temperature distribution in the pipe. Okay, this is the temperature of surface Ts. Okay, and inner side, the temperature is Ta. Oh, no, sorry. This is Ta, and this is Ts. Okay. Inner side is Ts and Ta. Okay. We are consider about the temperature distribution between the inner side, outer side. The outer side temperature is Ta, and the inner side is Ts. And we develop a rate of energy transport. Okay. So we are thinking about very thin shell, and the heat is conducted through this shell. At this point, heat is conducted QRR, and the thickness is delta R. So the heat is exit, heat exits